That's okay. Okay, let's start with basic atomic theory. I'd like to do, before I even get to these notes, a little bit of informal review on how scientists have learned over the years what stuff is made out of. Okay, um, you guys have heard of matter before, because that's the word that we've got on here, right? Can anybody define for me what matter is? Anybody know the? Got it. Yeah, matter is anything that has mass. It needs to weigh something. Okay, and it has to take up some sort of space. For example, here's an example of something that's not matter: a vacuum. You guys ever heard of a vacuum before? Like say, like think in outer space, where there's like a particle here, and there's a particle there, and there's a particle over there, but you've got this big open area where literally there is nothing, right? Volume is taken up, but since there's nothing in there that weighs anything, that has any mass, that's not actually matter. Okay? Now, although something that has mass and takes up space is like the technical definition of matter, maybe here's a better one. Matter is just stuff, right? Like if it's a tangible thing that we can touch and see and feel, then that's matter. What is energy? Does it matter? No, energy is not matter. Energy is something that can transform matter, and you guys in physics will learn E equals mc squared. So there is that mass energy correlation, but like if I give something energy by throwing it, or if it has thermal energy or light energy, that's not matter, right? So we want to talk right now about the building blocks of life, which are matter. And in chemistry, we break them down to the elements, right, which is on your periodic table. Now, history lesson then. Back in the 1600s, one of the first models of the atom was presented by a guy named John Dalton. Do you recognize that name? You guys in physics, we talk about it a lot. Dalton had 4 points to his model of matter. The nuts and bolts of it is that he figured that all hydrogen particles must be the same as each other, and all carbon particles must be the same as each other, and that they are different. So hydrogen is not carbon, carbon is not hydrogen, but each hydrogen he thought was the exact same as the next hydrogen. He was wrong about that, because at the time he didn't know about something called a neutron. Right? But his building blocks for what he thought of as as a model of matter, was a good start, because it helped us get towards elements and saying, well, this is different than this, and this is different than this. And so they started narrowing it down, and we now know of about 111, 12, whatever they're up to, including those synthetic ones, different building blocks of life. Now, Dalton's model of matter lasted for quite a while until, let's look at you guys, who was next? Yeah, J.J. Thomson. And J.J. Thomson did an experiment which helped him figure out that Dalton was actually still incorrect. Dalton thought that an atom was actually as small as it gets. But Thomson discovered through an experiment that there's actually something smaller than an atom. Atoms are made up of protons and electrons. And Thomson discovered the electron, essentially. Discovered what we call subatomic particles. Now, I already mentioned, I think, all three of them at some point. Do you guys know the basic three subatomic particles? Proton, neutron, electron. And so it wasn't until the Thomson cathode ray tube experiment, if you've heard of that before, that they finally started to realize that there's actually smaller stuff than what's on our periodic table. Now, for the most part, they thought at the time, Thomson thought at the time, that a model of an atom was a positive-filled kind of core. Not a core is not a right word. A positive-filled fluid, and then interspersed within it were electrons. But that still was not all the way correct. It took until Ernest Rutherford did a gold foil experiment. Anybody ever heard of the gold foil experiment? Hopefully these are things you've talked about at some point. If not, it's not like the end of the world. You don't know this stuff. But Ernest Rutherford realized that there was a nucleus. Right? And through his experiment realized that in terms of all of our matter, all of our elements that we're talking about, there is a core at the middle where all of the protons existed. He didn't know about neutrons at the time. But all the protons were in the middle, and that the electrons are dotted around it around the outside. Now, they weren't really sure how the electrons fit around the outside, but he realized that there were two different parts to the atom. And then since then, there's been newer and newer revised models, but those are kind of some of the main things that got us to this part, where finally they started realizing how the elements fit, and they were put together in a periodic table. And the periodic table is really based on one of those subatomic particles. Which subatomic particle defines how the periodic table is organized? Not quite. Protons. because it's protons that give you what number you are, right? So that's my goal today, is we want to talk about all these basic different parts. So, okay, before I get to building on that protons, let me go through some of these notes here. So, there are 90 naturally occurring and 25 synthetic. Do you guys know how to tell the difference on your periodic table between a regular, naturally found in everyday life element and the synthetic ones? Rebecca? Yeah, can you guys find atomic number, where's the first one on there? Technetium, 43. You guys find number 43? Hopefully you're already aware that that 43, its atomic number, means it has 43 protons. There is a number down on the far right-hand side next to the 43 on technetium, which is 98. And you'll see how 98 is in brackets. Okay, so let me try to explain why this works here. All elements will have a certain number of protons, neutrons, and electrons. Okay, but there's things called isotopes where there's different numbers of neutrons, and so hydrogen could have 1 neutron or 2 neutrons or 3 neutrons, and so the average weight of all of those is known as a molar mass, is the number that's listed there for most elements, and most of the time those averages are to 2 decimal places. If you look at my big periodic table, it goes to like 5 decimal places, which is insane precision. That being said, synthetic elements, they only exist for very short periods of time, usually because they're radioactive, and it's not really possible to have different isotopes of them because they only last for like just a moment. So really all we can do is just weigh them to the nearest whole number. So technetium 98, we actually know how many protons and neutrons there are. There must be 43 protons in technetium, but if it's technetium 98, you guys know how many tell how many neutrons there are? 98 subtract 43 tells you how many neutrons there would be. And technetium only would last for just a mere millisecond. Usually because, like we learned in physics there, it's going to radioactively decay. So anyways, if you're looking for the synthetic ones, that's the tip-off. It's going to have brackets around it. It's going to be to a whole number. And the reason why is that isotopes don't really exist because, honestly, the element itself barely exists. We don't have the ability to put it on a scale and weigh it because it's already gone. It's already decayed into something else. Does that make sense? Cool. Okay, what other stuff should we talk about here? You guys have heard of the metals versus the non-metals, right? They've also been categorized according to very broad properties. I'm going to steal Manuel's here. On this side of the periodic table here are your metals. Now, I need to make a really important distinction. Metal does not mean solid. Metal does not mean solid. But in most cases it does. Okay. For example, here's some exceptions. Mercury is considered a metal, but mercury is most common found as a liquid. Okay. Whereas iodide is a non-metal, but it actually is normally found as a solid. So please don't mistake metal and solid as synonyms of each other because they're not. Right? Our metals are things that exhibit these properties, and most of them you probably know, but I want to point out 2 of them that are a little less common. Do you guys know what malleability and ductility mean? Go for it. You're on the way there. Anybody else want to take a step before I give away the answer? You're close. That's it. What'd you say? Yeah, malleability means that you can make a sheet out of it. Okay, like I can make a sheet of aluminum. I can make a sheet of iron. Does that make sense? I cannot make a sheet of oxygen gas. So if you can make a sheet of metal out of it, that's malleability. And I think that's where you're kind of going there, where a sheet of metal, you have the ability to kind of mold it a little bit, right? Like it's still somewhat rigid, but I mean, I can maneuver it around and make some. Does that make sense? Anybody remember what ductility means? Take a stab at it. Close. It will be able to conduct electricity because it can be pulled into wires. If you can braid it into a wire, that's ductility. So, and then a logical extension is it might be able to conduct electricity through that. So, I would say most of the rest of these words you guys are aware of, right? Like you understand what strength and durable and conductors are. So, but if you want to make a little note here, malleability, build it into a sheet of metal. Ductility, pull it into a wire. Those are your metals. Your non-metals, more or less, are the exact opposite. right? Like, I cannot make a sheet of oxygen gas. It's not going to happen, right? Chlorine gas cannot be a wire that I use. So the odd ones are the metalloids, and these are the ones that are kind of like half and half. They sometimes fall into one category, some in the other. The advice I'd give you is label these on your periodic table right now. So these are the known metalloids. You've got boron, silicon, germanium, arsenic. You guys know where to find these? Here's the little staircase line that we usually use to separate our metals and nonmetals. Just put a little note for which ones are metalloids, just so you know, because it's not usually stated on a periodic table which ones are which. Otherwise, we basically have three categories. We have the metals on one side, the nonmetals on the other side, and they usually bond with each other ionically. And then in the middle, you've got the metalloids, which are kind of they sometimes behave as metals and sometimes not. Okay, now the periodic table is organized numerically by protons. Okay, so atomic number 1 has 1 proton, atomic number 79 has 79 protons. Okay. Can you change the number of protons in an item and have it be the same name? No, you can't change the number of protons, but you can change the number of electrons. And so we often, although the order goes like 1, 2, 3, 4, 5, 6, 7, they have an order to them. We've also put them in like the table in the rows and the columns based on the electrons, because we can change the number of electrons matter has. So things can gain and lose electrons, and the reason why goes back to the Rutherford experiment. Rutherford discovered that all the protons are in a nucleus. They don't easily get moved out of a nucleus, but the electrons that are around it, you can move those. And so we've arranged things into groups and periods, and groups are the ones that go like straight up and down. And one of the things you'll notice about your groups is that many of these things have the same charge. I'll talk about charge a bit later today, but do you guys know where to find charge on your periodic table, like the 1 plus, the 2 plus, the... Okay, now most of the positive charges are listed. Very, very few, actually I don't think any of the negative charges are listed. Because you guys know where you'd find your negative charges, right? They'd be in your group 17, group 16. So it wouldn't hurt right now, if you haven't heard of this before, I'll use hand walls again here. The very, very, very last column right here is known as the noble or inert gases. You guys ever heard that phrase before? What's unique about the noble gases? They have a full outer shell, and because of that, they're stable, which means they don't, or bond. Yeah, for the most part, right? So all of these guys in the last column right here, they don't really have any charge. They should never bond. Xenon and krypton have been known to do so in really rare occurrences, but for the most part, all of these guys in the last column have no charge. Now, everybody in the second last column, known as the halogens, so you're talking fluorine, chlorine, bromine, and iodide, it doesn't list it here, but if you want to write it down, these are all usually a 1 negative charge. The reason why is that they're 1 electron away from a full valence shell. So these guys are usually -1s, which means that oxygen, sulfur, selenium, tellurium, those guys are usually -2s. Nitrogen, phosphorus, arsenic are usually -3s. And then carbon and silicon are usually plus or -4. Pause and talk about that for a second. Plus or -4. You guys ever heard of the octet rule? Most orbitals want to have 8 electrons in it. Now, if you have 4, you really have 2 different ways you can go. If you have 4 electrons, you can either try to get 4 more electrons. If you picked up 4 more electrons, you'd be a -4. Because you'd have 4 more negatives. So -4. But carbon and silicon can also lose their 4 electrons, which could make them +4 as well. It's actually why carbon is such an important building block of life. I mentioned yesterday we're going to learn about something called organic chemistry. Organic chemistry is based around carbon, and carbon is really cool because it can form 4 different bonds, because it can either lose its 4 electrons or gain its 4 electrons, the most of any possible element. And so it's actually in a very unique spot on the table. Boron is usually listed as a +3, by the way, if you want to write that one in there. Now, that being said, there are so many different valence states that this table right here only lists a few of them. If you want to look back at the far back periodic table, you'll notice that it often lists like a ton of different valence states. I should make sure I'm clear. Do you guys know what I mean when I say valence state? Valence state refers to like what sort of charges there are. Okay, like valence refers to the outermost electrons, and so it can either lose 1 or 2 or 3 electrons. It can gain 1 or 2 or 3 electrons, and that's what gives its charges. So, Sam, give me an example here. Can you find where's a really cool one? Tungsten. Can you see tungsten on the table? It's W. Can you stand up and point to it? Since you're right there. I know it's really far away, but he's going to point to tungsten. Tungsten has actually 5 known valence states. Can you guys see them off to the side there? Can you point to them? I believe there's like a +2. Can you see where I'm referring to? The +2, the +3, the +4? Can you guys see those there? Those are what I refer to as valence states. And if you want to take a peek at the big periodic table, this table here usually lists 1, maybe 2, sometimes none of your possible charges. But I need you to be aware that a lot of elements have the ability to be +3 or -2, or +3 and +4 and +5 and +6. So a table like that is way more thorough than this one. Okay, I digress. I got off topic. Those are 2 that you need to know. I'm doing them out of order, apparently. Noble gases and halogens. The other really common ones you need to know about are in group 1 and 2. Those are your alkali and alkali earths. Okay. What's the charge of pretty much everything in group 1? +1, and everything in group 2? +2, yeah. And that actually forms the basis of a lot of our ionic bonding, because if there's somebody with a +1, if you're +1, do you have extra or fewer electrons? Fewer electrons. If you have +1, which means you have, well, you're going to lose an electron. Where are you losing your electron to? Well, a guy who's -1. Because why is it -1? Because it took the electron, right? That's the basis of ionic bonds. We'll talk about that more tomorrow. Periods go the horizontal way across the table, and they're all about energy levels. So there are 7 known energy levels in your periodic table. You'll see them labeled on the big one over there. I'm going to stand back here. So I want to make sure you guys can learn how this works. This is energy level 1, hydrogen and helium. There's 2 electrons in that energy level. Then there's 8, the second one, 8 in the third one, 18 in 4, 18 in 5, and then 6 and 7 is where it gets super confusing. Because here's how the table actually works. It goes 55, 56, 57, 58, blah, 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 71, 72. To save space, rather than have the table be like this far across, they took like this little section right here that should have gone really far, and they just pulled it out and put it on the bottom. Okay? Because otherwise what the periodic table should have looked like is there should have been another big gap, like you know this big hole right here? There should have been another big hole right here. All of these elements stretch out for a really, really long ways. Does that make sense? So when you're reading your periodic table, it's almost like there needs to be a bit of an insert, like a zoomed in section. Right here, this is not one element. There's actually like 14 elements hidden right here. So go from here all the way through here, and then repeat it back up right there. So although some people think that there's 9 rows on the table, there's actually only 7. What's groups would they be in? In terms of groups, we don't actually count them as a group. We just call them the lanthanide and actinide series. So they don't really have like a group, so to speak. If you get to a high enough level of chemistry, we did this briefly in physics. So there are 4 types of orbitals: s orbitals, p orbitals, d orbitals, and f orbitals. And I showed you a YouTube video of how like sometimes those orbitals merge together. How do I describe this at this point though? They don't really have a group though. Does that make sense? I guess if anything, you could say they're all part of group 3. But they kind of, when we work with those ones there, you'll notice that like most of the ones in the bottom row are synthetic anyways. Like most of them are going to nuclear decay, and so they're not even stable. Like you're not going to find californium anywhere in the world, right? Because it's just part of a decay chain. Like it would have started as plutonium, turned into these 2 pieces, turned into these 2 pieces. So really, we kind of ignore them a lot in terms of whether they're in a group. Is that fair enough? Good question. Okay, let's move on because I got lots to get through. One of the things that I'm going to be very picky on, and I am super picky in my chemistry class, I always want you to write a state of matter after an element. Always. Okay, if you just write this, if you write me a chemical and you say that it was NaCl, and you just leave it there, I'm going to be correcting you. Okay, because to me this is like punctuation. Okay, it is super important to include a state of matter and say that it's either a solid or say that you've got chlorine as a gas. Okay, state of matters matter. Say that a lot. States of matter matter because it actually makes a difference. If we were to try to do a chemical equation and we wanted to use, say, liquid nitrogen versus gas nitrogen, it makes a huge difference. Right? Liquid nitrogen freezes us out at like negative 200 and something degrees Celsius, right? Maybe you've seen liquid nitrogen before. Like it can like flash freeze a banana in a second. Well, that is exceptionally dangerous if it was liquid nitrogen. Gas nitrogen, I'm not afraid of at all because I'm being bombarded with it pretty much all the time because you guys are aware, right? Nitrogen is like 70% of our atmosphere. So there is a huge difference between N2 gas and N2 liquid. So anyways, that's my little preamble here. Make sure you're very clear about states of matter. So in general, metals are solid. In general, okay? But like, please don't confuse them as though they mean the same thing because that's a more or less rule. Mercury is the exception. Now, most of your gases on the periodic table are your diatomic elements. So hydrogen, nitrogen, oxygen, fluorine are all diatomic, and they always come in groups of twos. Bromine and iodide are also diatomic, but they're actually in liquid and solid form. And you guys probably will be able to know this because if you have the color table, they're all in color anyways. So sorry if you didn't get a color table, then you'll just have to keep track of which ones are different. On the big table at the back, though, you guys can see the blue, the black, and the red, right? So that's your general way of telling whether or not it's a solid, liquid, or gas. Okay. Now, we haven't talked a lot about compounds yet because that's the point of tomorrow. A compound would be like a word, but in general, same concept. I need you to always put a state of matter. So for right now, because you're not really going to know for sure whether it's a solid, a liquid, or a gas, here's your general rules. Okay? And what I usually tell kids is if you don't know, this is so bad, this flies in the face of what I say. If you don't know, go ahead and take a guess. Because I actually would rather you write down a state of matter just for the practice of that. But here's the general rules. If it's an ionic compound, it's probably solid. It might not be, but if it's an ionic compound, go with solid. Okay. If it's an ionic compound being put in water, we're going to talk about this later in the course, but we're going to use AQ. Does anybody know what AQ stands for? Yeah, I'll write that out here. It's aqueous. So if it's just a compound by itself, go with solid. If it's been dissolved in water, go AQ. Then if it's a molecular compound, and you know how to name these ones, in general, if it's small, it's probably a gas. If it's like in the middle, it's like a liquid, and the bigger it is, the more likely it is to be a solid. So like, let me give you a couple examples here. Here is natural gas. This is methane, CH4. You guys probably will recognize methane. It's the gas that we would use to like heat your house. It's in gas format. Its chemical formula is CH4. It has 5 elements in it. 1 carbon, 4 hydrogens, so it has 5. In general, that's very small, so it's probably a gas. Whereas this is a type of gasoline, not the gas you'd put in your car, but it's a type of gas. See how there's 20 combined elements in that? More likely to be a liquid. And then here is wax. Oh, you guys can see there's, what is that, like 56, 66 different elements inside of it. And so the bigger it is, the more likely it is to be a solid. Okay, so I know this flies in the face of what I teach you when you write your tests, but I would rather you write a state of matter and it actually being wrong, but at least you've taken an educated guess at it because it is super important. Not all the time, but there are times when it is super important that you have the right state of matter. The states of matter matter. Okay, do you guys know the terms physical and chemical changes? What makes something a chemical change? Say that again. Ooh, I like that. You have a product. That's way more technical than I was going to say. I like that. I was going to say, you know what's a chemical change? When something new is made, right? And I think that the technical word for that is something new is the product. So let me give you some examples here. Here is a sheet of paper. It has some chemical composition to it, probably some carbons, hydrogens, nitrogens. Okay, I am now going to do this. Is it something new? It's been physically rearranged, but it still has the same carbons and hydrogens in the same molecularly bonded order. Okay? Now, I don't have a lighter on me, but hypothetically, I burn it, and this thing goes up. Now it's a chemical change. Right? Now, the carbons and hydrogens and nitrogens that were involved, those didn't disappear, but they have been chemically rearranged into probably carbon dioxide, water vapor, maybe some carbon ash soot. Does that make sense? So if you want to tell the difference between physical and chemical changes, one of the biggest pieces is that a chemical change involves something new. It needs a product. If it's a physical change, the chemical components aren't changing. Right? So like the example I have there is freezing water into ice. If you can reverse it really easily just by changing the temperature, that's not a chemical change. So our goal is to talk mostly about chemical changes in this course, but we will mention physical changes. The reason I bring this up though is that states of matter, your solid, your liquid, and your gas, if you convert between your states of matter, you're talking a physical change. Okay? But in order to do a chemical change, you might need the right state of matter. Let me give you an example. This would be really extreme, but you're trying to drive your car. Right? What state of matter does the gas in your car need to be? Well, we actually put it in as a liquid, but it probably combusts as a gas. If you were to take a solid, like let's say it was minus 200 degrees outside, and literally the gas in your car turned into a block of frozen gas, would that combust? No, right? Now the combustion is a chemical reaction, but converting from the solid ice version of your gas to the gas version you need to combust, that's a physical change. So they do go hand in hand, but there's a distinct difference. So I want to make sure we're aware of the two. So what we're getting to then is we want to be able to talk about chemical reactions where A and B turn into C and D or something like that. Again, like I've been saying here, first I need us to be able to walk before we run though. So we need to be able to name what A is and name what B is. We need to be able to say NaCl, sodium chloride, AgNO3. Silver nitrate, yeah. What if I were to give you, let's try a few of these. You need to know this stuff. What if I were to give you NaClO3? Sodium chlorate. What if it was NaClO4? No, it's perchlorate. We'll talk about that. That's the point of this, is we need to review that. But hopefully you guys get my point here, is that we want to work on being able to name these words so that eventually the goal of chemistry is to say that element or compound A and B combine to form other stuff. That's where we're going eventually. Okay, really basic slide. You guys know these words, right? Reactants, products. You guys are aware of how we use those terms? So reactants are what you start with, products are what you finish with. Okay, if our goal is to eventually get to chemical reactions, another thing we should talk about are how will we be able to visualize, how will we know when a chemical reaction takes place? Two words I want you guys to be aware of, it's not written on the slide here, but I use them a lot, are qualitative and quantitative. And if you're in my physics class, I use those words a lot. So I'm looking at you guys in grade 12. Someone help me define those words for the rest of the group. What's a qualitative observation? That'll work, yeah. Doesn't involve a number, basically. It's something that you could observe that's tangible, but that you might not put a numerical value to, like color. It's red. Smell, pungent. It's whether it's transparent or opaque. You guys know those words? You guys know some of those words? Transparent, you'd be able to like see right through it, no color to it. Translucent, you can see through it, but maybe there's a tinge of color to it. Opaque might mean that there's like a solid cloudiness in it so you couldn't see through it, right? Those don't have numerical values to it. But another observation that would be quantitative would be, I might say that it has a pH of 7, right? There's a number attached to it. It's 30 degrees Celsius. There's a numerical value attached to it. So often we will need to talk about qualitative versus quantitative. In terms of qualitative, there are a few main ways that we can tell whether a chemical reaction takes place. Here or there. First one is properties have changed. Like, say, the state of matter, at room temperature, the state of matter, your melting point, your color, your density. Those are good indications that a chemical reaction has taken place. What color was the sheet of paper before I crumpled it up? White with some black on it. What color is it now? White with some black on it. Has it actually changed? No chemical reaction. Let's say I burn it. Well, then it's probably going to be brown, black, depending on how it burns. Right? A new color is usually an indicator of a chemical change. Okay, second thing, all reactions need to involve some sort of energy flow. We mentioned it yesterday. What are the two ways that energy can flow? What are the words we give to those two things? What if it requires energy? There you go, yeah. So you've got endothermic reactions and you've got exothermic reactions. All chemical reactions either give off or require energy. Every single one. Now, it might be minuscule. You might not even notice it. Like, it might be a very small amount of energy. It might be very, very large. For example, combustion gives off a huge amount of energy. Very noticeable. Whereas, like, rusting requires a little bit of energy. Not a lot, but just a little bit. Right? So sometimes you'll notice the energy changes, sometimes you won't. Okay? But they all have at least some give or take. You may also notice things like formations of gases or solids that appear. Those are usually indications of a chemical change as well. Okay, let's get back to where I started class, though. Let's talk about some of the scientists I mentioned. So we've got John Dalton in the 1600s. He decides to present a theory that all matter is more or less an element. He didn't use that word, but he says hydrogens are hydrogens, carbons are carbons, nitrogens are nitrogens. And every nitrogen is the same as every other nitrogen. Was John Dalton correct? Not quite, because he didn't know about the neutron. Right? Each nitrogen has the same number of protons. How many protons does nitrogen have? 7, because it's number 7. Right? But this nitrogen could have 5 protons. This nitrogen could have 5 neutrons. This one could have 6. This one could have 7. He didn't know about the fact that neutrons could change things. Now, he also didn't know that there were subatomic particles whatsoever, because it wasn't until later that we figured out the protons and electrons bit. So I really want to focus on that development and how we're able to use it to figure out atoms and ions and protons and neutrons and really be able to classify matter a little bit more specifically. So if we want to focus on atoms, like I said earlier, there are the 3 main types, right? You've got your neutrons, which are neutral, protons, which are positive, electrons, which are negative. And here's the first thing I need you guys to know. If we are talking about an atom, protons and electrons are the same. If I use the terminology atom, you have the same number of protons and electrons. So let me give you an example. Let's just do this one verbally. If I ask you about a sodium atom, how many protons are there? Well, sodium's number 11. There must be 7 protons. And if it's a sodium atom, there would also be 11 electrons. Now, does sodium actually want to have 11 electrons? If you've learned this before, no, it doesn't. That's 1 too many. So a sodium ion would then have ditched one of the electrons. So an atom is neutral. An ion involves someone gaining or losing electrons. I want to make sure we're really clear on that. Now, if I were to give you a sodium atom, do you know how many neutrons it has, though? Not without telling you more information, because a sodium atom or ion, either one, could have 10 neutrons, 11 neutrons, 12 neutrons. Right? Does a neutron affect the fact that it's sodium? What makes it sodium? It's protons, yeah. Now, if I want to make it a positively charged, can I add an extra proton? Then it wouldn't be sodium anymore, right? If I add an extra proton to sodium, it's now magnesium. Right? So if you want to change whether it's an ion versus an atom, you change the electrons. If you want to change what you call it, you change the protons. If you want to change its weight, you change the neutrons. Say that one more time. You may even want to write that down in some sort of way. If you want to change what you call it, you change the protons. We name it based on its protons. If you want to change whether it's an ion versus an atom, and like what ion it forms, you change the electrons. Either give it more electrons or take electrons away. That changes whether it's an ion or an atom. But if you want to change its weight, not every carbon weighs the same thing. Some carbons have 6 neutrons, some carbons have 7, some have 8. So if you want to change its weight, that's neutrons. And that's the reason why on your periodic table, like say for sodium, sodium is 22.99. You know how sodium has to have 11 protons? If it has a weight of basically 23, there are probably 12 neutrons. Right? Because 11 plus 12 would get you basically 23. But there are some sodiums that probably have only 11 neutrons. And that's why that 22.99 is like an average of what you typically would find in the world. But any one given atom has to have a whole number of neutrons. Does that make sense? But when you're looking at them in a large group, these decimal numbers on there are what the averages are. Okay. So, let's continue talking along these lines here. So let's talk about your ions. The valence electrons, the outsidemost electrons in the valence shell, they're what help you figure out what sort of ion could be formed. Right? And so, where are we looking here? Atoms want to have filled valence orbitals. In general, we sometimes refer to the octet rule, where it wants to have 8 electrons. So if you've got someone who's got 7 electrons in their most outer shell, they want 1 more. If you've got someone who's got 6 electrons in their outer shell, they want 2 more. Right? That's how we know that it's got a -2 charge or a -1 charge. You guys know this? I'm getting a lot of nods here. I'm gonna move on. I feel like I'm going too slow. Have you guys ever seen a picture like this before then? Where it shows like the electrons? So hydrogen, its most likely charge is probably +1. The reason why its most likely charge is +1 is that it's got 1 electron and it wants to lose that electron. If it loses that electron, hydrogen, by virtue of it being hydrogen, has 1 proton. It was supposed to have 1 electron. That was neutral, right? But if it loses its electron, now it's just got the +1 to it. Does that make sense? Or if I were to go over to here to fluorine. Fluorine is supposed to have 9 protons. Why? Well, that's why we call it fluorine. Fluorine has always got 9 protons, which means fluorine should have 9 electrons. And as I count them out, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. But there's a hole right here. There's an open spot for an electron. And so if fluorine picks up 1 more electron, now it has 10 electrons versus 9 protons, which means fluorine's charge is usually -1, because it's got 1 more electron than protons. Can fluorine lose a proton to become negative? Why not? Because then it's not fluorine, then it's oxygen. So let's do some examples here. I've got a chart here. Let's talk through some of this stuff here about protons, neutrons, and electrons. And you've probably done these before. I just want to make sure I'm really clear on it because we need to know our ABCs before we get to our words. So if I tell you that you have carbon 13, right off the bat, a warning bell might go up and say, hang on a sec, next to carbon is the number 12.01. Chris, why is there a 13 there? Well, 12.01 means I'm talking about like a whole whack of carbons, and the average carbon weighs 12.01, right? But this particular carbon weighs 13, right? So here, we're talking about large groups of things. Here I'm just talking about just one-offs. What does this 1 carbon weigh? So this particular carbon weighs 13. So let's start here. Its atomic number is 6. Why? Well, that's what carbon is. Carbon's number 6, right? Now its weight is 13. And I know that because I told you how much it weighs right here. How do I figure out its protons? It's 6. How do I figure it out, though? Yeah, it's the same thing as your atomic number, right? Protons defines what we call it. Okay. So then neutrons just requires very basic subtraction. If there's 13 total weight and 6 of them are protons, by default, there better be 7 neutrons, because 13 minus the 6 gives you the 7. What about electrons? Why don't electrons count? Say that. Say that. Not that. Electrons have a charge. Think physics. They don't weigh anything. In terms of weighing things, you would need to have at least 1,000 electrons to weigh 1 proton. You guys remember doing masses in physics last year? Protons and neutrons were to the minus 27. Electrons are the minus 31. So that's 4 units of magnitude difference. So you'd need at least thousands of electrons to be worth 1 proton. So electrons weigh so little, you'd never even notice. It would be like you go to weigh an elephant and a bird lands on it. Like, it makes no difference, right? Like, the elephant weighs, 2,000 kilograms, and the bird weighs 4 grams. You know what I mean? Like, it's not noticeable. So all we care about then is protons and neutrons. So let me try one more, then I'll have you guys finish the table if you haven't already. Beat me to it. Sodium 25. Again, sodium, if you look in the periodic table, is actually 22.99. Which means if we're talking about a sodium 25, we're talking about a particularly heavy version of sodium. This particular sodium atom just happens to have a lot of extra neutrons on it. In a way, it's kind of like a fat sodium. It's got a little extra girth to it, that's all. It's just got more neutrons. Its identity, though, is based on its protons, right? You get the idea. Okay, so anyways, sodium, by virtue of it being sodium, is number 11. Its weight is 25. How do I know that? I told you it. I'm going to have to tell you. Its protons then are 11, so 25 minus 11 gives you 14 neutrons. You guys ever done stuff like this? Okay, try the rest of the table here if you haven't beat me to it, and I'll fill it in a second. Grab some water. Well, I gotta do basic math in my head here. Thanks, Emma. 64. We're done. Gadolinium. Oh, why am I looking at that? 64 and 43. All right. Let me know if you don't get the same thing I do in the table. Don't look up until you're done, but when you're finished, just check your work against mine. Anyone have any issues? Does this make sense? Okay, well, let's move on to the next table here then. This next one here focuses more on the electron side of things. So the previous one was all about protons versus neutrons. This next one here is about atoms versus ions. So one more time to make sure I'm clear. An atom is neutral. An atom has equal protons to electrons. Okay. That being said, there's only one group on the whole periodic table which is usually found in an atom form. Take a stab at it. Which one is usually in atom form? Noble gases, because there's no reason for them to gain or lose electrons. Everything else has a strong tendency to either gain or lose some electrons and become ionic, which is actually really good, because think about this for a second here. If everything in the world was neutral, there'd be no reason for this thing to stick to this thing. Now, that's where solids come from, right? Literally, our physical structure depends on the fact that almost everything on the periodic table can be broken up into pluses and minuses, because pluses and minuses will want to attract each other, and if enough of them attract each other, mass gets built up in a solid form, therefore we have stability to us. If everything in the world was a gas, we couldn't exist. You get what I'm saying here? So like, thank goodness that the only thing on the periodic table happens to be the noble gases, and everything else can make ions. We need them. Okay, so let's talk through this first one here. K plus. Right off the bat, how do I know whether it's an ion or an atom? The plus, right? Because look right below it. This chlorine right here doesn't have a plus, so I'd be referring to a chlorine atom, who is probably looking to gain an electron as soon as possible, right? So potassium, by virtue of being potassium, is number 19, which means it has to have 19 protons, otherwise it's not potassium. But if it is a positive, it only has 18 electrons, because it's lost an electron. Does that make sense? To become positive, you lose an electron. And so then you have a charge of +1. Okay. Chlorine, in order for it to be chlorine, it's number 17. Chlorine is defined by its 17 protons. But if it's a chlorine atom, like this one has no charge here, it has 17 electrons. It does not want 17 electrons. It desperately, desperately wants one more, which is why chlorine is fantastic for bonding to things. Probably the most common thing you'll know that chlorine bonds to is sodium. What does sodium and chlorine make? Yeah, NaCl is salt, right? And I mean, that's a nice solid structure, right? Salt is vital to humans, even if you take a biology class, right? Like salt is something that's an important part of the human body. Sometimes you need more of it, sometimes you need less, right? You talk about osmosis and diffusion and those sorts of things. So, all right, let me do one more, then you guys finish the table. Cl minus is almost the exact same thing. It has to have 17 for both, though, because that's what defines it as chlorine. But now if it has a negative charge, it's because it's picked up one extra electron. Who gave it its electron? Probably sodium or potassium or someone like that who wants to get rid of its electron. And so that's how it gets its -1 charge, because it has one more electrons. So why don't you guys finish off the table here, and I'll just complete it too. Just don't look up until you're done. You guys have done this before at some point? It's good to hear. I really like to hammer this in on day one, though, because I find that if kids don't understand the basic structures of the protons, neutrons, and electrons, and the three things that they do, protons identifies who you are, electrons gives it the ability to have charge, or maybe not, and neutrons affects its weight, especially on like a grand scale. If you get those concepts there, then that's a good building block to go forward from. So. Okay. Let's just talk through my notes just on ions, but I think you guys get the concept here. This is just rehashing what we just talked about then. Atoms have the same number of protons. Ions have either gained or lost. So this is how we show that. But I've already talked about that, so I think we're good. So here's a picture to help kind of represent the idea. Here is a neutral sodium. It's got 11 of both. But a sodium ion has lost an electron, and so this is the lost electron, right? It's kicking out the electron, giving it to somebody else, because sodium doesn't want it. Chlorine wants it. And then, oh, I should point this out. Here's the terminology. Have you guys heard these words before? Cation and anion. Cations are positive, anions are negative. The best way I've ever heard to remember this is cats have paws. So cats are positive. Cations are positive. So if you can't remember cation and anion, cats have paws. Those are really clever. Here's a picture of anions. Okay, last thing I should mention. This is my last slide, correct? Finally made it to the end. Okay. I mentioned the term earlier. The official term is valence state. A valence state tells you what sort of charges can be formed. There are some transition metals, the ones in the middle of the table, that can form more than one charge and still be stable. There are some things that can gain 2 electrons or 3 electrons or lose 2 or 3. So I need you to be aware that there are many things that have more than one state, like mercury. Mercury can become a +1 or a +2. Both are something that is stable enough for it to work with. So your periodic table will only list 2 valence states. If you go look at the big one, I tried to have Sam point this out earlier, some of them have as many as 5, right? That tungsten one that you pointed to, there's like 5 things listed there. Okay. Your periodic table lists them in order of which one is most common. So if you want to look at a couple of examples here, find mercury. It's number 80. Do you see how mercury lists the 2 plus and then the 1 plus? You might say, well, why didn't they go in order and go 1 then 2? Well, it's because the 2 plus version of mercury is more common than the 1 plus. Okay. Whereas if you were to look at lead right next to it, 82 or 2 over from it, it goes 2 then 4. So it doesn't put them in numerical order, it puts them in order of most common. Okay, so just be aware that there are different valence states, and those are super important because I already brought up a couple of these before. If I gave you AuCl3, that's gold 3 chloride. I'll even write that out. This is what we're doing tomorrow. If I give you AuCl3, this is gold 3 chloride. That 3 means that you're using the 3 plus version of gold. Okay? And that's super important because gold could also be AuCl3, which would be gold 1 chloride, which would be the 1 plus version. So it makes a difference because those are different elements. Those are different. They have their own unique properties. What's the difference between them? Well, this gold right here versus this gold right here, one of them has 2 more electrons. Which one has 2 more electrons? Which one has more electrons? Yeah, this guy right here. This guy has lost 3 electrons. This guy's only lost 1 electron. So there is a difference. Chemically, one of them has fewer electrons. Okay, so the details really matter in chemistry. I'm going to harp on that a lot. States of matter matter. Roman numerals matter. The little subscripts, the big numbers there, all those little details that are like punctuation in terms of like the English language analogy of learning to read, they can make the difference between you being correct or incorrect. And in a real world scenario, they can make the difference between disaster and what's the opposite of disaster? I guess in chemistry, not disaster. I wouldn't say success, but like what you normally expect and like a whoops, that wasn't supposed to happen. We don't want whoops, that wasn't supposed to happen in chemistry because, like I said yesterday, like I really do think that if done incorrectly, the chemistry lab is one of the most dangerous places in the building. Right? The chemicals that I have sitting in the back there, like if there's a fire in the building, that's disastrous, because of the way that some of them could react under heat or pressure or when they combine with each other. So, okay. Anyways, I digress. I got off topic a few times. How'd you guys do today? Was that something somewhat familiar? You learned something new maybe here or there? Okay. I don't have homework for you. Okay, like there's nothing assigned, but I would recommend if you feel like you need the practice, and maybe even if you don't, I gave you guys some booklets yesterday that have tons of worksheets in them. I would do that for your own benefit, okay? Just so that you kind of get in the habit of things, because I really want to preach this fluency thing, okay? But I don't have anything due. So, I mean, you guys have, what time do we have, like 10 minutes here? I mean, if you want to go somewhere else and do something or print off notes, that's fine. If you want to use the 10 minutes, use that too. Okay. One last thought. I'm going to call you out a little bit here. You left. I have no problem with someone leaving, but can you guys write your names on the board when you do? So like Naomi, she just got up and needed to go somewhere. I have no problem with that. If you guys need to leave right now and you're taking off early, just throw your name on the board, would you? So anyways, I'm done for the day. You guys can do what you need to. So